Let's go through trig integrals. Remember, we have our standard integrals. Sine goes to minus cos, cos goes to sine, sec squared goes to tan, tan log of, or minus the log of cos or log of sec. But now, let's look at those, first of all, sine and cos to some power. I'm going to go through the sine ones. Remember, the cosine ones are exactly the same except minus the complement, that idea. So you still use the same techniques. Power of 1, well, that's just sine x, so okay. Minus cos x, not a problem. Sine squared, we saw how to handle that. We use our double angle, half of 1 minus cos 2x, and we get that one. Raise the power 1 more. Sine cubed, what will I do? I'm going to rewrite it as sine times sine squared, which will allow me to rewrite the sine squared as 1 minus cos squared. And I've now got it in the form of derivative times function, that sort of idea. If you don't see it straight away, I can do a substitution. U equals cos x. To u is minus sine x. And I get minus 1 minus u squared. Add 1 to the power over the power. In fact, whenever it's odd, approach it the same way. Because if it's odd, you can always write it as sine to the power of 1 times sine squared to some power. And then that sine squared you can change to 1 minus cos squared, and then you can do your substitution, u equals cos x. So odd powers, that's how we'll handle it. Even powers though, we do it this way. Sine to the power of 4, I can go sine squared squared. But for the sine squared, I'll use the double angle result. We're squaring it, it's no longer a half, it's now a quarter of 1 minus cos 2x all squared. Expand it out, and then each of these individual bits. Now you notice I've got another cos squared here, so I'm going to have to use double angle again, so half of 1 plus cos 4x, but we've now got something we can handle. So for even powers, you can always write it as sine squared to some power, and then use the double angle, expand out, and then you're going to get another even power in there. In this case, we've got another squared where we use the double angle again. Obviously, the higher the power, the more times you're going to have to break that down. Sine to the 5, okay, odd power, so say, we'll pull out the sine x, I can rewrite that as sine squared squared, change that to 1 minus cos squared, now I can just do a simple substitution and get up. Okay, but what happens if you have a combination of both? Sine to the power of something and cos to the power of something. Yeah, usually it's just going to be a basic substitution, either u equals sine x or cos x, just depending. Something like this. Cos to the power of 5x times sine cubed x. I can rewrite it. Sine cubed, again I'm using that idea of let's pull the sine out and I'll change the sine squared to 1 minus cos squared. I've now got derivative times function. Substitute in, we have it. So when both of the powers are odd, doesn't really matter which one you manipulate, but you pull one of them to the power of 1 out, creating one of those trig functions is going to then become to an even power, which you then can say is, well, I did it as sine squared was 1 minus cos squared. I could have just as easily have done it by pulling cos x out, leaving me with cos to the power of 4, which I could have written as 1 minus sine squared squared. It's going to be easier to pull out of the lower power. In other words, the substitution will end up being, will be the higher power. So I end up doing the u equals cos x. So if you've got two odd numbers, pull the power of 1 out of that lower power there. This time I've got 1 even and 1 odd. Well, I'll rewrite the cos x as 1 minus sine squared. Again, I'm just pulling out the power of 1. So same again. Pull out the power of 1, and I've got my substitution. So pretty much the same idea, but it must be the odd one we take it out of in this case. What if they're both even then? I can't now pull out the 1, so I don't worry about that. I just change one of them to be in terms of the other. So the cos squared I change to 1 minus sine squared, and then we've got ways of handling both the sine squared and the sine to the power of 4. I've cheated because we've already worked out that answer. I just wrote down what they were straight away, and there we go, we've got the answer. Let's look at tan then. I'll do tan, again, cotan being the complementary ratio, the same technique. Tan's a little bit nicer. Tan, well, minus the log of cos. We get the tan squared I can change that to sec squared minus 1, and those we can integrate. Get to tan cubed. Well, tan squared is sec squared minus 1. So I can rewrite this as tan x times sec squared minus 1, split it into two integrals. One of those integral will be times sec squared, which is derivative times function. The other integral will just be another tan function, in this case minus the integral of tan x. There's our answer. Does it change when we get to the even power? No. I'm going to do exactly the same thing. I've got to pull out, so notice what I'm doing is I'm pulling out tan squared. I'm not pulling out tan to the power of 1. So on that first one, that might not have been obvious because it was tan cubed. One of those things was tan, one of those things was tan squared. But it's the tan squared I'm pulling out. So I can change it to sec squared minus 1, pull it into two integrals. One's going to be times sec squared, so I can always write it as derivative times function. The other one's going to be some tan integral. And we get our tan to the power of 4. So tan, it doesn't matter what the power is, we do it the same way. Let's have a look at sec, or cosec for that matter. So sec to the power of n. Integral of sec. Well, how do we get log of sec plus tan? And this is how we get it. We just do multiply top and bottom by sec x plus tan x. Obvious, really, isn't it? Okay. Why do that? Because look what happens when I expand the top out. I get sec squared, which is the derivative of tan x, plus sec tan, which is the derivative of sec x. I've got derivative on function, therefore it's a log of sec plus tan. Now, do I do that every time? No. I should remember the integral of sec x is the log of sec plus tan, but that's where it comes from. And if they had asked me to derive it, well then that's how I would derive it. Sec squared, well that's nice. That's our standard integral, it's just tan. Sec cubed, I will split it into two things, sec and sec squared. But this time I'm going to use integration by parts. U is going to be sec x, something I can differentiate. So it'll be sec tan. dv will be sec squared, something I can integrate. It becomes tan. That's uv minus the integral of v du. I now have this integral of sec times tan squared. But the tan squared I can rewrite as sec squared minus 1. Split that into two integrals. I get minus the sec cubed x, we'll come back to that, but plus the integral of sec, which we know is the log of sec plus tan. Alright, back to the integral of sec cubed. Well, that's what I was trying to find. So I now see it as an equation. I'll move that to the left hand side. 2 times the integral of sec cubed, therefore divide everything by 2. We get a half of sec tan x plus a half a log of sec plus tan. So odd powers, we're going to have to do it by parts, like that idea, split it up into 2. You're really going, please give me an even power. Because we get to sec to the power of 4, that's just so much easier. Because I can write that as sec squared times, well, sec squared, which is 1 plus tan squared. Do a substitution, it's just 1 plus u squared du, and there it is. So our even powers, always just pull out the sec squared, and then you can write the other sec squared as 1 plus tan squared. It's going to be to some power. So evens are nice. Odds, bit of work to be done. So 4g, they're the basic ideas behind how to approach our trig integrals. And the power will tell you the technique to use.